So what I will talk about will be Sobolev embeddings on the Gauss measure space, and there is one more keyword which I didn't put into the title, but maybe I should say it now. So the additional keyword will be Orlicz spaces, so there will be all the Orlicz spaces in this talk, and so basically my goal is to give some sort of an overview of some Gaussian Sobolev embeddings in the Orlicz context. So I will not necessarily be trying to focus mostly on my own results, but rather give an overview of what is known. But nevertheless, there will be some results which I co-authored together with Andrea Čanke from Florence and with Lebesgue from Prague. So we will notice probably at some point that the results I will be talking about are about 10 years old. So I haven't been really working on this recently very much. But also I would like to go back in the near future to some related problems, so I think it is a good opportunity for me to give this talk and sort of remind myself about what has been done. So now let me start. I will start with something which we have seen a lot throughout this workshop, which will be the logarithmic Sobolev inequality. So let me start by defining the Gauss measure. So it is the measure on Rn, which has this particle density, and the constant in front makes the corresponding measure space to be probability. And I will introduce the following notation. So if I have an integrable function on Rn, I will suppose to actually say like integrable with respect to the Gaussian measure. So let me say it now. So if I have such a function, then I will denote its integral average with respect to the Gaussian measure, like this u with subscript gamma m to emphasize that I'm taking this measure. And so this is my formulation of the logarithmic Sobolev inequality. I think I am the first one maybe using this notation, like in this conference, but it is sort of still the same inequality, just a different formulation. So what does it say? It says that whenever we have our function u whose weak gradient belongs to L2 with respect to the Gaussian measure, then and say that it has mean 0. So in that case, u actually belongs to this Sobolev space. Now can you see it? Maybe it is better seen now. So actually this says that U has a slightly better integrability than just L2, and slightly better by the first power of logarithm. So now I haven't introduced this Orlicz space yet, technically. So for now I'm just saying that these are the functions which are contained in this space. This is not a norm in this space, but I will go to Orlicz spaces and how to define their norms in a moment. And so now maybe about the goals of this talk, which I already mentioned briefly a bit earlier. So once again, we have this logarithmic Sobolev inequality, which we have seen, and what are the generalizations I want to talk about? Right, so the first generalization which I will present, which is now quite classical, will be replacing this L2 on the right-hand side by a more general LP. So say that P is between 1 and infinity. But I want to go much beyond this. So the next stage could be that we replace this L2 by a space of exponentially integrable functions. This is again something I will have to define properly, but these are functions which, if we put them into exponential, then they will be integrable with respect to the Gaussian measures, then I'm suitably formulated. Now, so I promise that I will actually be more general, so I will consider general Orlicz spaces. So what this is, so here these LP spaces, they are defined in terms of a norm which involves raising absolute value of the function to a power p. So there is some like sort of p power function involved. Here there is some exponential function involved. And Orlicz spaces, they would allow you to actually use any convex function in thing. Right, and so in fact, the results which I will present, they are actually more general than that. So they deal with general so-called rearrangement invariant Banach function spaces, in case you know what it is. If you don't know, you can sort of forget about it, but I'm just saying that the formulations are more general than what I'm really saying here. Now, yeah, so I also want to talk about my own contribution to the study of these problems, and they do not lie in the setting of first-order embeddings. So I will also talk about higher-order generalizations of this inequality. So more precisely, we will have higher-order derivatives here on the right-hand side. Yeah, so this is the plan for the talk. And now we are actually at the stage when we can define our main function spaces, which will be the Orlicz spaces. So we will always start with a given so-called Young function. So what is that? So this is a convex function on 0 infinity, which is supposed to be left continuous and should vanish at 0, and it shouldn't be like identically 0. Right, so now if you take a look at this definition, so different people could choose different definitions, and I think that even the same people would sometimes choose different definitions, so that's okay. Now I'm allowing for the function a to actually have infinite values. So this could be useful at some point. I will mention this in a few moments, how this is useful. Yeah, so before that I should define the Orlicz space. Now, so here we have some probability measure space, Sm. In most cases throughout this talk, this will be just the Gauss space. However, sometimes it will be the interval 0, 1 with the Lebesgue measure. And so this is why I want to define these Orlicz spaces for a general probability measure space. Now, this Orlicz space, it is denoted like this, so L and A goes to the exponent. Sometimes I also write the measure space here. And yeah, so what is this? It is a bit, it is not so straightforward to define a norm on the Orlicz space. So it is not as easy as with the Lebesgue spaces, where you raise the function to the power p, then you integrate, and then you raise to 1 over p. So we could try to sort of take the function, put it into A, and then integrate and take the inverse, but this does not really produce exactly the thing which we would want. So in particular, if you imagine that this function A is an exponential function, then it could make a difference whether you have a constant inside or not. Because if you have a function f, it could happen that integral of e to the f maybe it's not integrable, but if you take e to the f over 2, then maybe it will be integrable. So it is important to sort of allow this freedom of a constant inside. Yeah, and this is the way how you define the norm. This is called the Luxemburg norm. Now what? Yeah, so examples. So the standard examples are the p power function, where p is less than infinity, and then the corresponding Orlicz space is indeed the LP space. Yeah, so now you may wonder if I can actually recover L infinity. And since I allowed for this infinity here, then I can do it this way. So basically, I will need my Young function to coincide with infinity, well, somewhere close to infinity. If I want to get exactly the L infinity norm, I do it like this. So for a while it is 0, and then it jumps to infinity, which is allowed in my definition, and this is how we recover this space. And now I will also introduce some useful notation which I will use throughout this talk. So it is good if you try to remember it. But I think that the notation sort of suggests what it is by itself. And maybe one thing which I should point out here. So we are on a probability measure space, in particular on a space with finite measure. And if I am here, And if I do not care too much about constants, which for this talk I do not care as long as they are dimension free, so it doesn't really matter how my Young function is defined near the origin. It only matters how it's defined near infinity. If you define it near the origin in any other way, it will just sort of result in an equivalent mode, so it doesn't matter. And so I want to define this space. It is denoted LP log L to the alpha, and indeed it corresponds to a Young function which coincides with t to the p times logarithm of t raised to the alpha when t is large. Right? When t is small, this does not necessarily make a very good sense. It vanishes at 1, but it's not a problem. And second notation I want to define, and did I already use this space? I think I used it in the motivation, so now it is defined. So if A is the Young function which coincides with e to the t to the beta near infinity, then the corresponding Orlicz space is denoted again like this. Right, so these are the main examples I will be working with. And now we can try to see some particular cases of the logarithmic Sobolev inequality in the Orlicz setting. So unfortunately what will be happening is that if I choose some Young function which is far away from LP, then maybe the logarithm will not quite appear explicitly. So it may not be logarithmic anymore at some point. Right, so let me first talk about the general LP setting. So the L2 result, I already mentioned, this was due to Gauss. As far as I understand, when p is strictly between 1 and infinity, this result was known a bit earlier and by the work of Lebesgue. I don't know French. Yeah, but I think that his main contribution was to obtain the endpoint p equal to 1. And formally, the inequality looks as you would expect, sort of, when you know the L2 case. So on the left, we have a space which is slightly better than just LP. It is LP log L raised to the power p over 2. So again, the phenomenon which we have here is that sort of the degree of integrability of the function itself is slightly better than the degree of integrability of the gradient. So I should be emphasizing everywhere, but I will be forgetting about this. So all these constants in these inequalities, they are dimension independent. They are allowed to they are, however, allowed to depend on other parameters. So in here, they depend on. Now, so let us take a look at the case when p is equal to infinity. So this was studied by these three authors, 1994. And here the behavior is sort of much different. Right? So if I have my function whose gradient is in L infinity, then the function itself suddenly is not in L infinity. Right? So this by itself, I guess, is not surprising if you think about it. So say, if we have our function which is equal to, say, x1 on the whole R, and then its first order derivative is just constant 1, so it will be in L infinity, but it certainly is not bounded. On the other hand, it has still relatively reasonable integrability properties because of the decay of the Gaussian measure near infinity, so it is still exponentially integrable with respect to the Gaussian measure. So now we may wonder what actually happens if I now put the exponential space. Whether maybe I get equality, but this unfortunately is not exactly the case. And it turns out that there is still a slight loss of integrability between the gradient and between the function itself. So let me present this case with functions which are exponentially integrable when raised to the second power. This appeared in a paper by Bobkov and Goetze in 1999. And it turns out that there is a slight loss of integrability. So here is the second power here is only f first power. You can have a general beta here. Then what is this? I think it is something like 2 beta over beta plus 2. In any case, if I have general beta positive, there is still a slight loss in integrability. Now, I can talk about one thing, it is relatively useless, but you may wonder about it. Maybe one note before this. So all these inequalities I mentioned here, they are sort of optimal in the sense that if I take my space on the right-hand side as something fixed, and I look for the best possible Orlicz space on the left-hand side, it is the one which I wrote here. If you know what rearrangement invariant spaces are, then these are actually even the best rearrangement invariant spaces. So now this result may be somewhat useless. At least one of the authors claims that it is the most useless result he has ever proved. And so this is what Lebesgue was saying at some point. Right, so they wrote some paper about which I will be actually talking a little bit more. And there was one side result in this paper, which is this one. So they managed to find a Young function such that if your gradient belongs to this Orlicz space, then the function exactly belongs to the same space and nowhere better, but nowhere worse. And so this Young function, it is somewhere between powers and exponentials. So it grows less fast than exponentials, but more quickly than any polynomial, right? And so, yeah, this space is actually even what we could call self-optimal. So if I start with this space on the right-hand side, then on the left-hand side, I can't get anything better. And it works also the other way around. So I could start with this space on the left and look for the best one on the right. This is the same. All right, so now let's maybe try to make all this more general. So let's try to find some general framework which would cover all these results. So there is this problem. I start with my favorite Orlicz space LA. And I want to find the optimal Orlicz space which will be associated with a different Young function in general, unless we are in the situation as previously, which will be denoted by AJ. And so we want to find the best possible one for this inequality to hold with a constant which does not depend on the dimension. Now, so this problem was resolved in the article I was just mentioning by Andrej Čanky and Lebesgue in 2009. So maybe I will show you the construction of the optimal Orlicz space, which will be somewhat technical, but then I will also talk about how you get it, which will maybe be less technical, hopefully. So in order to construct this optimal Orlicz space, we first need one more notion, which is the notion of the Young conjugate. Right, so if you know your Hölder's inequality for LP spaces, so you have two spaces on the right, one is LP and the other one is LP prime. So Young conjugate does exactly this. So it gives you the second Orlicz space which should appear in the Hölder's inequality. So this is a formula how to get the corresponding Young function, and this is the example I was already mentioning. There is some normalization needed. It doesn't matter too much if you are like me and don't care about constants, right? So if you start with LP, then the conjugate will correspond to the space LP prime. Now maybe something more interesting. So if you start with an exponentially integrable function, so this is a function which is relatively, or the space is relatively close to L infinity, then the conjugate will be relatively close to L1. So the Young function will be equivalent to this t times some power of logarithm near infinity. So I guess these are all these examples I had in mind for this. Now there will be this construction, you don't have to remember it, but it is good to know that it is you know, if you ever need it, it can be found in the paper. Right, so you start as follows. So we define an increasing function e on 0 infinity like this. So this is the inverse of this function. So you have to take this function. Maybe, I mean, you have probably seen this function here throughout this workshop already. If not, I will tell you how it is related to the Gauss space. And so you have to take the norm of this in the Orlicz states related to the Young conjugate, and you do not take it on 0 infinity, but you take it on a restricted interval from 1/3 to infinity. Yeah, so you get some function, and then the Young function we are looking for, which describes the best possible Orlicz space in our inequality, is given by this formula. Yeah, so now let me maybe talk a bit about, you know, how you can possibly do anything like this. And so this inequality can be obtained as a consequence of the Gaussian isoperimetric inequality. So we have seen this at least quite precisely in the talk by Joris on Monday, but I will repeat something anyway. Yeah, so if I start with a measurable subset of Rn, I first have to define some notion of the surface measure or something, like, you know, the measure of the boundary, which I can define as follows. So this thing, this is not the usual boundary, not the topological one, but the so-called measure theoretical one. I mean, these people in measure theory, I think they call it essential boundary of E, and then you integrate over this set with this density and with respect to the n-1 dimensional Hausdorff measure. And so the isoperimetric problem in the Gauss setting says that we should find among all measurable subsets of Rn, of a fixed Gauss measure, those who have the smallest Gaussian perimeter. And so you will not be surprised if I tell you that the solution of this problem are exactly half spaces. Now, yeah, so this is a theorem which we have also seen, I believe. So the Gaussian isoperimetric inequality, which was proved by Borel and I believe independently by Surakov and Sirson. And in order to formulate this result, so the result is here, but it involves some strange function I. And we have to say what it is. So this is so-called isoperimetric function of the Gauss space, so how it is defined. First we consider this function phi. So for a given p, we look at this particular half space. So this is the half space which contains all points whose first coordinate is at least t. Then we sort of measure it with respect to the Gaussian measure, so we get some function on the, sure, this should probably be defined on R, right? Yeah, I just wrote for t positive, but this should be defined for any real number t. And now once we have this, we can start this sort of thing, which is our isoperimetric function, and isoperimetric inequality takes exactly this form with minimizers being the half spaces. Yeah, so now about this function I. So it is called the isoperimetric function, as I said. And so since I'm not so interested in the constants, yeah, so I mean it is very nice that it has this explicit formula. But for me, this explicit formula may not be so useful, and so what is more useful for me to know how this function actually behaves, and it behaves like this. So this will be useful if we go 1 or 2 slides back. So you could see something similar over here. So here is our isoperimetric function. It just somehow got to the denominator in our formula. So now, Yeah, so how do you actually proceed further with the argument? So how do we make use of this Gaussian isoperimetric inequality? So there is some procedure which is called symmetrization, which you can do in various contexts, and it turns out that you can do it in the Gauss context as well. So let me do the following. I start with my measurable function u on Rn. And by this u with circle, so this will be called sign non-increasing rearrangement of u with respect to the Gauss measure. So what this is? So this is a non-increasing, decreasing. So this is a decreasing function, but not on 0 infinity. It will be on 0, 1, because the measure of the Gauss space is 1, so just on 0, 1. And it should have the same measure of level sets as the original function, but now the measure of level sets here is measured with respect to the usual Lebesgue measure. Here it is in Rn and measured with respect to the Gauss measure. Right, so this function u circle somewhat describes the integrability properties of u with respect to the Gauss measure. Yeah. And so now the symmetrization, I actually want to construct another function which will be defined again on the Gauss space. And I, however, construct it based on this one-dimensional function. So I just compose it with my function phi, which was defined on the previous slide. So what is useful to know about this? If you do not remember the definition, that the function u and its, I call it Gaussian symmetral, this u with the full circle, they have the same measures of level sets. So from this point of view, they are the same, but this function here, it is much simpler, because it only depends on one variable, on x1, and in this variable it is decreasing. So one can deal with that much more easily. And so this symmetrization, how it is connected with the Gaussian isoperimetric inequality, it basically sort of follows the form of the minimizers. So the level sets of this function, they are half spaces. This is sort of what we need. Now,
sorry, what is phi again?
So phi is this function here.
Oh, yeah, okay.
Yeah.
All right, thank you.
Yeah, but you don't even need to remember this. You just remember that it is a function of x1 decreasing in this variable and the same measure of level sets.
So just to make sure that I understand, basically you just take the values of u, the highest values, and you push them to the left until you have until they're all like in one level, and then you push the next values and so on. That's
I mean, if we are in one dimension, we do exactly what you said. So you take the values and you push them to the left. Now if we are in more dimensions, we need to sort of be maybe more careful, but ideologically this is what is happening. Right. Yeah, so now I will show you something which at least I call a Pauli-Segre principle in the Gauss space. So maybe what is the classical Pauli-Segre principle from the 50s? So this is a principle which says that, I mean, if you have a function on Rn with respect to the usual Lebesgue measure, then you can again symmetrize it. But if you do it with respect to the Lebesgue measure, you should respect the usual isoperimetric inequality. So the functions should be radially decreasing now, because the level sets should be both. And so if you do this, then the norm of the gradient decreases. And you do this, and on the Gauss space it also works, but you have to do everything with respect to the Gauss measure, and you have to use the correct symmetrization, which we introduced on the previous slide. Now what is good? So since we are studying these Orlicz Sobolev embeddings, so our symmetrization preserves Orlicz norm, right? Because it preserves the measures of level sets, and Orlicz norms, they do not see anything else. So it's good. And how about gradient, so the norm of the gradient actually decreases, or I mean does not increase under symmetrization. So it seems to me that this was already sort of established in this paper by Erhard, but again this paper is in French, so I wasn't able to check it very, very carefully, but I think he sort of already has this Orlicz setting. Now, I mean, about this paper I'm talking about, so they have something slightly more general, so they are able to do this, to prove this inequality when LA is replaced by a more general so-called rearrangement invariant space. So for instance, if you know Lorentz spaces by any chance, then these would be allowed here. Now, so why is this all useful, or what does it tell us in connection with our embeddings? So basically it tells us that we can reduce everything to the situation in one dimension. So in a way, this function u with the full circle is the worst possible one when we study Gaussian Sobolev embeddings. So we can just throw away all other functions and just study what is happening for these functions, and since we have this, then we know that what is happening will be sort of the same thing as what is happening for general functions. So this sort of stuff tells us that we will be able to reduce our dimension-free Orlicz Sobolev inequality to some one-dimensional inequality. So now here is a theorem, which was proved in this 2009 paper. Again, they have more general function spaces than just this LA and LB, but let's formulate it like this. So we have two Orlicz spaces, LA and LB, and we are interested in the validity of this estimate. And it turns out that this is completely equivalent to a certain one-dimensional inequality written here. And so this inequality, it doesn't have any Gauss measure anymore. So basically everything was now rewritten with respect to the Lebesgue measure, which I mean, after some calculations you can do it. So on the right you have just some function f. So this is the same Orlicz space, but you just take it on the interval 0, 1 with respect to the Lebesgue measure instead of with respect to the Gauss measure here. Again, the same Orlicz space, but on 0, 1. And so here is some sort of an operator which has this isoperimetric function of the Gauss space in the denominator. And so now in particular cases you can sort of characterize when this is valid. Yeah, and apparently they were able to get this description of the best possible function space on the lab here based on this one-dimensional inequality. So after some calculation, you can also get to the result I was mentioning before. Yeah, so now we actually get.
And in the previous slide, did you have a parameter t alone? I missed.
Yeah, here. Yeah, so I mean here this is some function on 0, 1, and the function depends on t.
Okay.
So it is.
Yeah, sorry, thank you.
Yeah, I think that people often get confused with this. So I mean one could try to just write this dot. Yeah, but I mean it is a bit strange to write a dot in the bound for an integral, so we usually write it like this. But I admit that this is a bit confusing. Yeah, so now we come sort of to the topic when I joined this project, which concerns higher order embeddings. So now the question you could ask, or the program you could ask, would be that we want to prove a variant of the previous result for higher order embeddings. And in particular, there is some sort of a question. At this point, I don't give like a precise meaning to it, but you could ask whether it is possible to get optimal such embeddings from isoperimetric inequalities, whatever this means. Right, so what is the difficulty here? You could try to symmetrize again, but this is complicated because the symmetrization in general does not preserve higher order differentiability. So if you symmetrize a function which is differentiable up to second order, you may end up with something which you can't know, which you can no longer differentiate twice, and you will be in trouble. So this method typically does not work here. So what one could try to do, since we already know our first order embeddings, then maybe to get a second order embedding, we can just try to iterate the first order twice. You will certainly get something. The question is whether you get something reasonable or whether there is some loss of information throughout the process. Now, what it turns out, so I decided to talk about Orlicz spaces, but it turned out that this was actually, in a way, this was what I wanted, but in a way, it was a bad thing, because this loss of information may appear if you just work in the context of Orlicz spaces. Here, actually, I could be lying too, so I'm not completely sure, because I am aware that this loss of information appears if you work in the Orlicz context, say on regular domains in Rn with the Lebesgue measure. So I do not have the corresponding examples on the Gauss measure, and in a sense, the Orlicz spaces seem to be sort of more general, like more nature on the Gauss measure space than on these Lipschitz domains. Like even on Lipschitz domains, if you start with W1P, then the optimal Orlicz space is this LP star, but you can improve it in the setting of more general spaces to some better Lorentz space. In here, if you start with LP, the optimal Orlicz space is LP log L to the P over 2, and this is the best possible one. So if you use some other Lorentz spaces, this will not give you anything better. So I'm not completely sure if the Orlicz setting is like wrong here, but in general, this does not seem to be the best one if you want to iterate without losing anything. Yeah, so at this point we really had to use these rearrangement invariant Banach function spaces, which I'm not going to define. I will maybe tell you that these are function spaces which just depend on the measure of level sets of functions, and they should be monotone, so if some function is pointwise bigger than some other function, it should have bigger norm. Yeah, but there is like no explicit description as in the Orlicz setting. And so we realized that if we work within this framework, then the loss of information actually does not occur. Right, so in a way, we are able to obtain optimal higher order Gaussian Sobolev embeddings from isoperimetric inequalities, because the first order ones are obtained from them, and then we just iterate. Right, so now I will show you maybe some more technical slides with our results. So this is sort of the main result. So we have two young functions A and B, and I will be talking about embeddings of order m. So there is this parameter m, which is an integer, positive, and there are two statements which I claim are equivalent. So the first one should be a dimension-free, higher order Gaussian Sobolev embedding. So all these functions U here, so this will not hold for a general function, because of course if my function is a polynomial of degree at most n-1, then this right hand side will vanish and the left hand side not. So I have to impose something, and so I will assume that the function has mean 0 and its derivatives up to order n-1 have the same property.
So what's your notation for nabla m? So you have a vector of all derivatives? How do you?
Yeah. So this is, I think I can introduce this. So this is the vector of all derivatives of order m, and then I take, I guess, the Euclidean norm of that, and then I can put it in the equation. Yeah, so there are two bad things in this notation, and in fact there should be like another thing. But just for simplicity, I denote it like this. Yeah, and so it turns out again that this n-dimensional inequality with a dimension-free constant is completely equivalent to some one-dimensional inequality. So this was the simplest description we were able to find. So in this unstrange operator, I'm not sure if you are, I mean, it will be probably more difficult to really like characterize boundedness properties of this. However,
1 second. Why S? Who is S?
yeah, so is there S?
Or is S?
Yeah, so S is not here, maybe it is T. Sorry. Yeah, I mean, I was copying from our paper and there was S, and then I decided to use T, so S is T. Yeah, in any case, I'm afraid that this is maybe not super useful. So in a moment, I will tell you how we got it and maybe how it really work if you want to get particular, like specific examples. Right, so, I mean, there is one further equivalence. So, this is the first order operator, which we have seen in connection with the first order result. And how we got basically our embedding, we got it by taking the first order embedding and just iterating it n times. So you would naturally expect that you get your operator t, but just like composed n times with itself, which is what happens, but then, I mean, if you try to sort of write down how it looks, it will be a nice streak. So we managed to get this simplification, which should be equivalent to this. And still, I think it is relatively useless. So in practice, it is probably better if you really just take the first order embeddings and you iterate them n times. And if you have like a reasonable example, you can probably do it. I will show you some examples, like some particular ones at D. And let me see what else we have. Yeah, so we should talk about the necessity of this result. Let me maybe recall what it was, because there was an equivalence, and the iteration process, it gives us sort of one direction. It gives us the direction from here to here, going through the first order case. But you may wonder whether this one implies this. So whether this is sort of the best possible thing. And for this, we have to test on some specific functions. So on some functions having specific form. And now we will really like follow what the isoperimetric inequality tells us. And the isoperimetric inequality tells us that it is probably best to test on functions which just depend on one variable. So we do that. There is some particular formula here. So what you can see here, so this is basically our operator, the first order one. We can compose it with itself m times. Now the issue is that the operator is on 0, 1, and we need our function to be on the Gauss space. So we have to compose everything back with this function phi, which I recall gives us the measure of, the measure of the half space, where the first coordinate is at least t. And so this way we sort of transform from the interval 0, 1 back to the Gauss space, and we get some test function. And after some calculation, it turns out that this one really shows the sharpness. What else do I have? So I have these examples that I promised to. So there will be several inequalities, and as was the case before, so if a function u appears here, then it is assumed that it has vanishing integral, and also all its weak derivatives have vanishing integrals up to order n-1. Now, so here are our examples. So we can try to start with LP less than infinity. So if we iterate, or if we have first order embedding, we remember that what we got was LP log L to the P over 2. And now, if you want to prove this, you would then again start with LP log L to the P over 2, which I didn't mention as an example, but it turns out that like each iteration would add P over 2 here, and you do it n times, so you get NP over 2.
Is it gradient m?
No, sorry?
In number 2.
Sorry. So all gradients are of order m. I was apparently copying the first order one. So this is a misprint, yes. So in number 2, we start with L infinity. So what is it? The first iteration gets some sort of an exponential space, and then we would further iterate these exponential embeddings n times and end up with this space. So you can see, as previously, that in the first case there's a gain of integrability if the space is just LP, so it is better than better than exponential. But if we are, if we are here, then it is the other way around. So we are losing in integrability, and also if we just start with some exponentially, with the space of exponentially integrable functions, we are also losing a little bit, as before.
Number 1, suppose that you wanted to end up in LP, so does it also work? Kind of my naive guess would be to put the negative power of the logarithm on the right hand side. So.
This should be the case, I guess.
In order to avoid these conditions that the lower derivatives have been zero, what should be subtracted from U?
I mean, one could try to subtract some polynomial.
Some polynomial?
Yeah.
What is this polynomial?
I mean, it should have coefficients which depend on the integrals of the derivatives.
You need to expand U with respect to Chebyshev polynomials in order to find this polynomial. Just more generally, in order to have such inequality without any condition on U.
Yeah, I think it is possible to subtract some polynomial and then the coefficients.
In order to find this polynomial, you need to expand U with respect to Chebyshev polynomials.
Yeah, maybe. We actually had something like this in our paper, because I mean this was one formulation which we had. And then we had like an actual Sobolev embedding, and so there was like a proof of the equivalence of them, which involves subtracting some polynomial. What else? So again, the function spaces on the left-hand side are optimal among all Orlicz spaces, and in fact among all rearrangement invariant spaces in this case. Do I have something else? So in the last few minutes, I can tell you that actually, even though I was talking about the Gauss space, then this method is much more general. So if you want to study Sobolev embeddings in some other context, you can do so with similar method very often. So our procedure basically, let me remind you, consisted of 2 steps. So in order to get the first order embeddings, you need to employ some sort of symmetrization, and then to get the higher order embeddings, we just iterate. And so this 2-step procedure works more generally than just on the Gauss space. Actually, even in the paper I was talking about, we had more general applications. So of course you can deal with regular domains equipped with the Lebesgue measure. Like on this, there were like previous results known before. But anyway, you can do it with this method as well. Then, we were able to deal even with some less regular Euclidean domains. And if you have a domain like this, so the Sobolev embeddings for such a domain, they are worse than the usual ones, but you can still characterize them using this procedure. You don't have to just have your Gauss space, but you can consider more general product probability spaces, and the same procedure works. Now, some applications which were not in our paper, but appeared later. So Zdeněk Mihola in 2021 used this on the entire Rn with the Lebesgue measure. So there is some difference that now the space has infinite measure, but you can still do something similar. Yeah, then I mean, he was interested also in other cases. So he was able to deal with the hyperbolic space, for instance. And maybe to finish, I will tell you that you can even like consider embeddings of fractional order. But we only did this on Rn with the Lebesgue measure. We didn't do anything on the Gauss. Yeah, but generally this procedure would apply after some modifications. So our embeddings are now fractional order. So if the fractional order has, say, between 0 and 1, there is some way how to do the symmetrization. And then to get the higher order embeddings, you combine sort of this fraction embedding for order between 0 and 1. And yeah, you iterate with integer order, I think. And so you combine these two to get higher order fraction. Yeah, so there are other applications of this procedure. And that's the end. Thank you.